And we're broadcasting. There we go. So all of this stuff, generally speaking, has to do with finding the distance from a point to a line. This is where the normal vector tends to come into play because the shortest distance between a point and a line is always perpendicular to that line. And so if we're able to use the normal vector, it's already perpendicular. So quite often we wind up projecting onto that normal vector to find the distance between a point and a line. It's a little trickier in 3 space when we're dealing with lines. So sometimes we're looking for a little clue that helps us that way. So here we have a line, 5x plus y plus 8 equals 0. That is our scalar version of the line. We want to know the distance between Q, which is -4 and 3, just kind of arbitrarily chosen, and the line. So here's our technique. We know what the normal is to this line. So the normal to this line is 5 and 1. That's right. We just look at the scalar values and we know, based on those coefficients, what the normal is. So the normal is just a line that's perpendicular. It could be anywhere. Oh, there. Playing hard to get all this time.
I was checking my email. I just got one at 11:13.
I wonder if I didn't send the other one or something. So
I don't know.
Oh, the internet, eh? Sometimes the electrons get lost. And so we'd actually just started, and I was just doing that little discussion with Lindsay here, the fact that quite often we use the normal vector to help us determine the distance between points and lines, because the shortest distance is perpendicular to the line. Often we're using projections. And this other thing where it's tricky in 3 dimensions to use the normal vector to the line, because it's not unique. So anyways, we started with our 2D example, and this is just the CEMC lesson by and large. I've tacked another example onto the end. And the other example is from number 6 of the exercises. I thought it would be good to go over it. Anyways, we have a line here, Q4, -4, 3. Here's our scalar version of the line. The normal vector is just taken from the coefficients of the scalar. And the normal vector is just arbitrary. It's any place. So what we need to do, we need to choose a vector and then project that vector onto the normal vector. And that's going to give us that distance from Q to the line. So we need to pick just any point anywhere on the line. So we're going to pick a nice handy one, point P. And we're just going to use the y-intercept of the line. So when x is 0, y is equal to -8. So 0 and -8 is going to be our arbitrary point that we're going to choose.
Okay.
And we're going to make a vector. What's going on? Oh, I said -8. Yeah. Just already making bad mistakes with my signs. Okay. And then we're going to project that vector onto the normal vector. Okay, this is where you're probably going back and you're saying, gee, it's May, and I kind of forget how to do the projection of QP onto the normal vector. Okay, so that distance is going to be equal to the projection of QP onto the normal vector. Okay, and we've been using the dot product to find really handy ways to take the dot product and project it a line onto another one. So QP dot the normal vector divided by the length of the normal vector is the magnitude of the projection of QP onto the normal vector. So this is what we're after here. And QP, it doesn't matter which way I go, but I guess I'm going to go from P to Q. Yes. So 0 minus -4 is going to be my x value for my Cartesian vector, and -8 minus 3. And so QP is 4 and -11. My normal vector, I know what it is already. And so QP dot n is 4 -11.51. And that's going to be divided by the magnitude of n. (4.-11) is 20 minus 11 over the square root of, and so my x is 5, so it's going to be 5 squared plus 1 squared. So 20 minus 11 over the square root of 26. So 9 over root 26. So it's 9 root 26 over 26. And if you like, you can put units on there. So we projected an arbitrary vector QP onto our normal vector, and that's given us the perpendicular distance from the line out to point Q.
Okay. That's good.
All make sense?
Yeah, that makes pretty much mostly sense. Yeah, no.
Okay, yeah. So just a procedure. Once again, you'll see we're using our dot product. We're doing that trick of finding the normal vector out of the scalar equation. We're going to be doing that again when we deal with the scalar equation of the plane, because it also has a normal vector that's based on the coefficients. All right. That was a remarkably two-dimensional example. So let's step this thing up. We're going to 3 dimensions where there are no good normal vectors. All the normal vectors in 3D are bad. Okay, so here we go. We have our line. And so our line is going to be given by x, y, and z. And x is 1 plus 2t. So we're starting out with the parametric equation. Y is 3 minus t. And z is -1 plus t. So there's our line. And our point Q is 4, -1, and 1. So there's our point Q. This is our line in 3D. And I gave you a little example of, well, it was actually exactly this example. And the problem that we have is that the normal vector between, there is no unique normal vector to this line. So there are a whole bunch of normal vectors that basically aren't parallel to each other. You can spin it right around the line, right? So there are a lot of non-parallel normal vectors. So our normal vector trick that we used in 2 dimensions isn't going to work in 3 dimensions, okay? So definitely there is a normal vector, but we just can't read it directly from the line. So there are a few techniques we can use to get around that issue of not having a normal vector to project onto. So here's what we're going to do. We're just going to do the same thing where we pick an arbitrary point on that line and we get an arbitrary vector. If I can find this length from P0 to Q, and I have my direction vector for the line, I can actually project PQ onto my line. I can find this length, and if I know what QP is, I can find that length, and then I can just use the Pythagorean theorem to find out what the length of the normal vector is, okay? So I'm going to use a point here. I can choose it arbitrarily. I can figure out what QP is just using the coordinates. That'll tell me the length there. I can then project this onto the the direction vector of the line. And the length of the projection is the second leg of this triangle. And I can figure out what the normal vector length is between point P and Q. Okay, so it's sort of a three-step process. Okay, I'm going to choose my point based on the position vector for the definition of the line. So P naught, I'm going to let be 1, 3, and -1. And a direction vector, and the direction vector I used for the definition of this line is, who can tell me that just looking at the parametric equation? Are you able to see it, Jeff?
Yeah, I'm just here. I was just.
It's probably tiny on your screen.
It's a little smaller. It's okay.
So this is 2, -1, and 1. So that's my direction vector here.
Gotcha.
So I'm going to be projecting onto that. Magnitude of PQ is going to be the projection of P naught onto D. And the projection of P naught onto D is P naught Q dot D over D. All right, so let's get busy here. Oops, P naught Q, yes, no, I'm doing the right thing. Let's go from P to Q. So 1 minus 4, 3 minus -1, and -1 minus 1, dot the direction vector over the magnitude of the direction vector. There we go. So this is going to be my projection. Just going to pop up here to finish out the math. So -3 and 4, -2, dot 2, -1, 1. There, I'm all ready to do the dot product. -6 minus 4 is -10, minus 2 is -12. And the magnitude of the direction vector is 4 squared plus 1 squared plus 1 squared. And so this is the square root of 6. So 2 root 6. Okay. Uh-oh. Lindsay's looking at this with great trepidation. Yeah, and so we could get a negative value for our dot product, and we just want to use the absolute value of the dot product. Okay. Yeah, so we could get a negative length. That wouldn't make any sense. Okay, method 2. And this method is more elegant. So this method actually looks a little bit more like what you would expect to see in kind of a calculus algebra course.
Okay.
Okay. So basically it looks like this. So we have our direction vector here. Uh-oh, and I just erased my direction vector. So we have our direction vector 2, negative 1, 1. And we have some vector that we're not sure about going from Q to P. P has the coordinates that are defined by the line. So we don't exactly know what P is, but we do know it follows the formula 1 plus 2t, 3 minus t, negative 1 plus t. Q we're actually given. Oh, what was the value of Q? 4, negative 1, 1. I got too vigorous in my erasing there. Okay. So P is somewhere. If QP is perpendicular to the direction vector, what's true about the dot product? So if I manage to pick my P so that it's perpendicular.
Yeah. So then it would equal 0 then.
Exactly. So my dot product is going to be equal to 0.
Okay.
Okay. So I can actually set this up. And what we're going to do is we're going to set the dot product equal to 0. And we're going to solve for t. Okay. So QP dot D equals 0 when QP is perpendicular. Which just means it's normal to the line. And so this technique is actually going to find us QP, which is then a normal vector to the line.
Okay.
And it runs out to Q. And so we're going to actually be able to find the length that way. So this one is a little bit more elegant. Okay, so QP is equal to 1 plus 2t minus 2 and 3 minus t minus negative 1 and negative 1 plus t minus 1. And we're doing the dot product with 2, negative 1, 1. Oh my goodness. And yeah, that's right. We're just doing the dot product with that. And it's equal to 0. So this looks like it's going to go swimmingly. So I'm going to simplify this QP calculation here. So 1 minus 2, negative 1 plus 2t, 3 minus negative 1, 4 minus t, and negative 1 plus t minus 1 is negative 2 plus t, dot 2, negative 1, 1, and that's going to be equal to 0. Okay. Oh, that is a negative. Okay. So now I'm ready to do my dot product. 2 times -1 plus 2t, comma, -1 times 4 minus t, comma, 1 times -2 plus t. Oh, yeah, okay. -2 plus 4t minus 4 plus t minus 2 plus t is equal to 0. Wow, this is going to be a miracle if I haven't made a mistake. -8. So just gathering up the like terms, -2 minus 4 minus 2 is -8. 4t plus t is 5t plus 6t is equal to 0. 6t is equal to 8. T is equal to 4/3. And I'm fully willing to admit at this point, I think I've made a mistake. Somewhere. Lindsay is looking very disappointed. Somewhere in here. But I have followed the correct procedure. Okay. Where would I go from here? Because I think I'm just going to leave this at this point. T actually should have a value of about 2, but I've probably dropped a negative sign somewhere. Oh, don't give me that. How would I find the distance now that I have my T?
So would you figure out what P would be?
Exactly. Yes. Okay. So I would substitute my T in here. And that would be telling me exactly what P was. And so P probably winds up being like 5, 1, and 1. So this tells me what my P is. How do I find this distance?
Do you want to use the Pythagorean theorem, could you?
Yes. Okay, so we've got that distance, that formula for the distance in 3 space. And so the size of this vector, actually, I can just find by doing the subtraction thing. So 5 minus 4 is 1. 1 minus -1 is 2. And 1 minus 1 is 0. So now I would be using the Pythagorean theorem, and basically this is going to be the square root of, it's going to be the square root of 5.
I got you.
All right. So that is a long, exhausting process.
Yeah.
See, actually, you're holding your head. Lindsay's holding her head. So there's just one thing I want to talk about, and that's to help you with exercise number 6, which is sort of a favorite of mine.
Alrighty.
So we'll set it up. So we have 2 skew lines. And so line 1 has position vector 2, -1, 3, plus t times 4, 3, 1. Line 2 is -1, 2, 1, plus s times 2, -1, 1. I'm assuming, oh yeah, these are definitely skew lines. And I can tell very quickly just by knowing that this one is not a scalar multiple of that one. Okay, so I can see definitely they're skew lines. I haven't accidentally gotten a couple of lines that overlap somewhere. Okay, so bad example because I'm drawing in 2 dimensions. They go by each other, they don't touch, but they are closest to each other at some point.
I see.
Okay. Now, the trick here is to find the one unique vector that is perpendicular to both of these. Okay, so somewhere in here, there's going to be a line that connects, or a normal vector that is perpendicular to both, and it's fairly unique. So, my question to you, how could I find a vector that's perpendicular to both of these lines? Did you just make the cross product motion? Did you
Yeah.
really? Yeah, that's right. We have a direction vector, okay, for each of these lines. And so if I take the cross product of these two direction vectors, basically, I'm going to find a normal vector for those two lines. So 4, 3, and 1 cross 2, -1, and 1 is equal to a normal vector to both line 1 and line 2. Okay, so those are the direction vectors. I take the cross product, and I've dropped the negative sign already. That is going to be the normal line to both of those skew lines. Now that's not good enough. I'm not done. I've only found a normal vector. The last thing I have to do is I have to project some vector, some arbitrary vector onto that normal vector, and I should be okay then. Just find the magnitude of the projection. Can you name me a nice arbitrary point on line 1?
Wait, oh. You could use the position, could you not?
Exactly. Yep. So I could just choose 2, -1, 3. It's just sitting out there on my first line. And then I can choose -1, 2, 1, which is the second position vector point on my second line. Now I've got the connection between those two. I have a normal vector, and I can do the projection onto the normal vector, and I'm going to find the distance between those two skew lines.
Okay.
And to prevent me just doing like a whole bunch of stuff at the board and then getting, you know, missing a negative, I'm going to let you guys do that. They have the two exercises actually. They have the two examples in question number 6, and they have the full solution too, so that you can figure out where the negative sign's gone wrong.
Exactly. All right.
Okay. So it's really raining. It's really supposed to rain tomorrow.
Oh,
yeah. So here was my plan. Tell me what you think. Oh, here. I'll just shut the stop.